But I'd like to introduce our speaker, Giuseppe Amatulli. He's coming here from Yale, where he is a research scientist and there for the last several years working on spatial ecology, GIS in particular. He runs a website, a really interesting website called spatialecology.net. I encourage you all to go to there. It's right there. And it's both an education and a research website. And a lot of the research he's looking at is trying to fuse data sets, from satellites to the ground and put it into a machine learning framework. So that's something near and dear to a lot of people's hearts, whatever your application is. And so I will let Giuseppe take it away. Thanks so much.
Yeah, thanks, and thank you very much for hosting this seminar. So today I'm going to talk about a hot topic in global monitoring of freshwater at high spatial and temporal resolution. In particular, we are trying to see what we can do it from a machine learning framework for approaching stream flow. What we can do and what we are in the term of in the theoretical question that we are trying to reply, and then going deeply in real practical assessment of what we can do with machine learning. So in particular, the water cycle, that is composed from different parts, and I will concentrate during this talk with the stream flow. But the same kind of approach and general thinking in the machine learning can be applied also to the other part of the water cycle. So I'm going to talk about briefly overview of the machine learning framework, where it is in the hydrological application, and see pro and cons comparing to the process-based model that everybody is using so far. So then I'm going to explain what we are developing right now. So with this ongoing project, and I will present the methodology that is implementing in the framework, and also talking about the ancillary layers that we need to build up in order to allow the machine learning to work properly. I will briefly explain the machine learning concept, which kind of algorithm we are going to use it, and we can see some preliminary analysis for water quality application. I will show also data visualization platform that we are building with another hosting partners, and we'll present the team with some conclusion. So let's focus first in the state of the art of machine learning, the process-based model. So you can see in this graph on your left why you have the process-based model that are using good understanding of physical and scientific interaction that are the different processes that are involved inside to the stream flow analysis and other kind of process-based analysis. Rather in the bottom part, you see what the machine learning using, especially in the core action of using data and big data. The machine learning is also call it as a data-driven model. So the algorithm is built not on physical-based approach, but from the statistic that the data are able to capture from the data. So in these terms, more you have variability inside to the data that are able to capture all the different combinations from the observation versus the predictors, you are able to explain all the different aspects even better than process-based model. So a general example, if you are predicting precipitation, but you don't have station in one particular ecoregion, so for example, the desert, and you don't have station there, the machine learning cannot predict what is happening in the desert. So if you are able to really having data sets that are cover the full distribution of the predictor and the different interaction, then the machine learning can understand the physics, the correlation between the different predictors. So far, in the process-based model, you have been using, many scientists have been using process-based model, and I put in the first, the one that are driving now in the United States, the WRF Hydro and the Rapid, and so on from other kind of institutions. So all these models, they use it, they are being used to go at 0.5 resolution and up, and as soon you try to modeling down in high resolution, they start to failing it. So rather in machine learning algorithm, we have been using machine learning in different kind of approach, not only hydrology like deep learning, long short-term memory, neural network, random forest, gradient boosting. So all these one, and there are also XJ boosting, another one. So there are other machine learning models that can be implemented. So as you can see, on the left side, we have the process base, and there has been a quite a good understanding and implementation from Dr. Gray and Herring from Alabama University that has been tested in local scales, the machine learning algorithm. When I talk about local scale, I've been testing a lot with, for example, with the camel model data set, I've been testing in catchment area, but I found only 2 articles that are dealing really with the stream flow at global level. So one, it was at 1 kilometer resolution using 6 different predictors from Barbarossa, and he was deriving yearly mean and maximum minimum. Rather, another one was 2014 from Beck at resolution 0125, and he was using a bit more extended data set as a predictors, but as you can see, they are missing, for example, water table, or for example, snow cover. So everything that is influencing the stream flow has to be put inside to the machine learning in order to have a good prediction. But when the process-based model and machine learning, when we have and what is good from one to the others. So the process-based model, they are built from bottom up, observing to the observed measurement pattern, and they are based on physical model. So we can do experiment. So for example, if there is a Barnett area, what is going to happen to the stream flow? So we can do experiment by tuning all the different parameters. But the limitation is human-based. Actually, I would say more department-based because it's driven by what the department was using the year before, and parameter calibration. So most of you probably have been playing a lot with this parameter calibration that quite often are parameter regionalization. So in stream flow, for example, one parameter that is quite often used is the roughness of the stream. So that one quite often, even in the last publication, has been used. Okay, let's use it 0.5 everywhere because we don't know how much change. And if we don't know some scientific aspect, we cannot insert in the process base. And then also there is an error compound that if there is one function in the if one function in the process base is missing or is wrong, and then it's going to be compound in the other implementation. Rather, from the machine learning, you have another kind of approach is built from top down. So it's really the data that are driven the correlation between the different variables. They can identify stuff that we don't know. So they can highlight situations that we still didn't think or we don't know. And it is extremely efficient. You can run neural networks a bit more long computation, but for example, random forest is quite fast. It can be overperformance in terms of process base. But what we cannot do, we cannot observe everything, especially if we don't have data that are covered, like I mentioned before, one term of the distribution of the pattern. They may be difficult to interpret. We can say why may, because there are different techniques that are now used to understanding how we can use the output of machine learning in this framework. And sometimes can be contrary to the physical flow, to the physical parameter that we are going to use it in process base. And one of we cannot simulate the causality of some interaction. So a work that is able to integrate high resolution and 90 meter resolution, working with a very big data fusion. I'm talking about 50 predictors that are driven the stream flow, and be able to later on, because we are pushing our research in this direction. Now we are pushing in the stream flow, but the real final aim, maybe in 5-10 years from now, is the combination of machine learning and process base in a unique environment to try to integrate both of them. So with this general introduction that is for for stream flow, but can be the same for other kind of application, from process-based versus machine learning. Our novel contribution is really a machine learning framework able to estimate the fresh water in terms of quantity and quality from large and small river. When I talk a small river, I start from 1 meter resolution to very huge river, at rivers and lakes, because they are working under the same concept. Global scale, so covering the full global, and by building up a fresh specific environmental variable that I'm going to call it stream variable at high resolution 90 meters. And then we are going to build up a web phrase interface for sharing the data and also to support decision making in the different quantity and quality of the water. So which is the final aim that we want to do? We want to really arrive to the point that we click in one particular river and we can get immediately estimation of the flow, meter cubic per second, or quality of the water like nitrogen in ppm in concentration, or phosphorus in ppm, carbon, you are testing carbon, also CO2 concentration, and then we can use some other process-based model to go from the concentration of nitrogen or carbon to the emission. And this is something that we are achieving also. So let's see how we can arrive to these parameters, or where we arrive with the framework that we are building. So in order to do a machine learning approach to simulate the stream flow, you need the three main components that I'm going to describe one by one. So we have Gaussian station in terms of water quantity and quality. This is the approach that is useful for any kind of machine learning. So you need observation about the phenomena. So you need where the phenomena is going to happen. So in our case, it's going to happen in the streams. So we need the high spatial resolution stream network. And then you need predictors. In this case, these predictors need to be compiled for the streams. And we are going to see how we are going to compile it for the streams. So let's concentrate in one by one, and we will framework how we are going to use it. So let's start with global watershed and stream network at high spatial resolution. As far as you know, the digital elevation model is very important for detecting small and large stream network. You can identify all the hydrological parameters like flow accumulation, drainage, direction, stream order, and so on, but you cannot identify water presence absence. So you can see where is the channel, but you cannot see if there is water or not. You cannot identify the water discharge and the water occurrence, but you cannot see with high precision the local location precision, because it's influenced rather than accuracy. Rather, from satellite observation, you can do more or less the opposite. You can see water presence, but not volume. You can indirectly calculate the volume, but you always check about the water surface. You can have a long time series of the water presence, and you can understand the water body weight or stream weight. But you cannot see, for example, small stream below 30 meters for Landsat, or stream connectivity. You can see the direction of the water, which stream goes inside one. And in the moment that you have a cloud or something that is masking out your water body, you don't know if that river goes where. So the combination of the two allow us to really complement the two information. And this is going to happen, is happening when Yamazaki released just one month ago the new Merit Hydro, where combined the stream, where combined the Merit, the digital elevation model that he built up, that was a combination between SRTM and a Japanese sensor, with the implementation of with the ancillary data like the Joint Research Center water occurrence dataset, in order to calculate a really accurate hydrological corrected depth. So he calculates flow accumulation and flow direction, but based on single flow direction. So I'm going to rebuild the model, using the Merit Hydro. I'm going to rerun the stream network using multi-flow direction, and in particular using the R watershed graphs. And something very particular, I'm going also to compute the full analysis under equivalent projection. We are going to see this projection that is quite new. I don't know if anyone heard about, but is very promising in terms of reducing a maximum the accuracy between distortion, especially in the northern part of the northern-south part of the two hemispheres. So now that we described where the stream is located, let's try to see how we are going to build up the predictors. So in this particular case, so as you know very well, if we have a gauging station over there in the bottom part over here, we need to take into account whatever is happening over here in order to estimate the stream flow. Okay, so this is quite a good understanding, but this gauging station, he knows the observation, but he doesn't know what is coming up. So if you have precipitation over here, if you have snow cover, if you have water present, if you have a farmer, a factory, agriculture in the upper part, is going to influence the stream in terms of quantity and quality over here. So we need to bring this data down to the stream in order to build up the machine learning. So in other words, we are going to calculate the stream, the basin, and transfer this information that is happening in all the basin over here in each single cell. So you are accumulating down this information that can be, for example, precipitation, or can be amount of concentration of forest or amount of agriculture in each single cell downstream. So it's a sort of flow accumulation. It's the same concept of flow accumulation down to the stream, but rather than accumulate the area, you accumulate the forest, let's say. So in this way, you have accumulated forest and accumulated agriculture in the upstream river. So we released a data set of 1 kilometer in 2015, covering hydroshed base, and we have done all the computation inside grass in the supercomputer at Yale. So we have been reproducing the full network by combining, by stream down, this hierarchical stream approach, climate, topography, topology, land cover, and so on. And we have been done the computation for 20 million grid cells at 1 kilometer in the hydroshed location. So now we are going to repeat the full computation but at 90-meter resolution. So let's see what does mean in a visual action what this information over here. So we take, for example, cultivated marine vegetation, and we can zoom in an area in the center of the United States. You can see in percentage over here. High percentage means high presence of agriculture, low presence of agriculture. So you can immediately see that the Middle West is pronouncing in presence of agriculture. So if we zoom even more over here, so what we can see, that stream that born, so this one is agriculture and this one is like forest. Stream that born, let's say, inside to agriculture will have a lot of agriculture content. Rather, streams that are coming from the forest will have much less agricultural content until they start to change because they are crossing and they integrate stream flow from agriculture. So this one is becoming our proxy, for water quality. And we are going to see the application of this in the machine learning framework. So with the same concept, I can build up every kind of predictor that is influencing my discharge, take into account what is happening in the upper stream down to the stream and transfer the information from the upper part down to the stream. So this one is going to be built. All this aforementioned methodology will be applied to the different predictors. And I'm going to build up a fresh specific environmental variable that we call the stream variable for the last 30 years at monthly level for all the 90-meter resolution for all the different land use predictors that influence snow quality and water quantity and quality, following the methodology that we have been describing 3 years ago. So this is quite an appealing data set that we are going to build that, of course, can be used for all the kind of application. So far, which are the data sets that I'm going to compile it to build up this computation? So I need to go back I need to have a full global coverage, 30 years of observation, multi-level, 90 meter or 1 kilometer if there are not a bit more, 525, that influence water quality. Then I'm going to pre-process, make a pre-processing standardization in terms of extent, pixel size, no data labeling, and so on. And we are going to reproject everything to AQ7 projection. In the end, we are going to do the stream computation down, accumulating down to each single stream in the world. And this one is the full data set, the data set that I'm compiling, the list under development, that influence the water quantity and quality. You can see climate with the terra climate or CHELSA, or you can say the different kind of vegetation like NDVI or gross productive production. You can find out the ESA land cover for the last 30 years, each single annual year. You can see livestock, for example, maps. You can also manure of agriculture, so in the agriculture field, and so on. All the different parameterization of the water, like the gravel from here, JPL from George Allen, the data set hydro lakes, or the global river width from Landsat, the global sulfur water from GRC. So everything that is a proxy of water quantity and quality. So, for example, I was discussing with some of you, I don't have yet snow accuracy, snow presence, even snow depth. So if you know some information about this, this grace is going to be over here for the water table fluctuation, even if it's a 3-degree resolution, but I'm going to try to use it. So in particular, there are also some data sets that we are building that are not existent, so we pre-building. In this case is the geomorphometry derived from the marine depth. So this is a data set that is going to be published soon, is under review. So I'm calculating 26 variable merit derived, so at 90 meter global level. Is going to be hosted in open topography. They just tell me a few days ago, so it's going to be just arrive with this information, and it's already in preprint. You can already download the data without problem, so you can read all the different documentation over here. And for this, I use it the AQ7 projector computation. So let's see what does mean using this, and what are the implications about the projection system that we are going to use. What we are using is what we are doing is very, you can see a lot of the difference in this graph. So you can see this graph in this way. You have 2 digital elevation models that are perfectly the same in the subtropical area in Costa Rica. Okay, over here, and you have the same one under UGS84 and here under AQ7. You calculate the slope for each one. This one for the AQ7 and this one for UGS84. Okay, so if you make a correlation between these two, they should be the same, and more or less they are. They are in the close to the equator, so the distortion is very moderate, so they are more or less the same. Let's see if we translate these 2 digital elevation models to the subarctic zone. This one, you can say the same shape than this, and this is the same shape this one, but is distorted due to that UGS84 and high distorted in the upper part. In other words, I'm transporting the Costa Rica dam inside to Greenland. Then I do the same, the slope over here, and calculate the slope over here. So I make the correlation, look what you obtain. The one-to-one is over here. What does mean? That everything under, even the simple slope, every time that you calculate the slope in UGS84, you are making an underestimation of the slope in the northern part compared to the equator. And if you think the slope, curvature of the soil, the curvature, first derivative, second derivative, everything, even the river network is influenced by the changing of the elevation. And this one has to be approached. If you do the AQ7 projection, this problem is minimized as much as possible, because you have the center of each of the projection inside each continent. So you have the Africa, North America, South America, Europe, Eurasia, and then Oceania, and then Antarctica. So the distortion are really, really small, in the border compared to what we are going to see. And just a dam, the density of the point, density, yeah. So you can see over here that the 1-to-1, so everything that is WGS84 at 20 become a 30 in merit, in under AQ7. So you have a continuous underestimation as soon you move up to the northern part. So this has to be taken into account. When I talk with the people in physics, they freak out that we are still doing geography in 2D and not in a spherical dimension. So let's try to move slowly in that direction with a projection that is less deforming the situation. And this is what the situation. Is that underestimate the slope because the slope is elevation versus distance, but the distance is changing at pixel level. It's changing when you go up to the north. Okay, so sorry, this one is come out a bit like this, but so this is the AQ7 projection that you see in each single continent. So as you can see, for example, you can see immediately that the Canada area is smaller compared to the typical WGS84. So everything that you calculate for Canada and Siberia area is going to be always overestimated of the WGS84. Rather, over here, we are minimizing as much as possible all their errors. And due to that, I'm doing this accumulation down to the streams. I want to have an equal area projection also for the northern part, because especially when my basin is going to be huge and go vertical like the Nilo, over here I will have a big deformation. I will accumulate small pixel with a larger pixel. These allow you to minimize as much as possible the AQ7 projection. But I know that, for example, Landsat use the sinusoidal, but that one is only AQ area. So this one is trying to minimize the angle distortion and also the area distortion and the dimension distortion. So it's trying to make a combination between all of them. So go back. Yeah, that one was going out. Anyway, so now going back to the full list that I'm going to build. So I'm really going to train a machine learning model. Let's see how big is going to be this table. So 30,000 stations coming from GSIM, from the data set, 12 months of observation, 30 years of observation versus 50 predictors that I described some of them over here. Plus, I have to take into account also 6 months in advance, especially for these predictors that are changing, like precipitation that in the snow cover, that what is happening in January, then is going to influence my discharge in August, especially for the snow cover. So then take into account the time lag that I have in the stream flow. So I need to take into account also the historical situation for 6 or even 7, 8 months sometimes. So I will take into account this one, not for all the predictors, but for the most important one. Probably humidity is going to be the same, but soil retention, for example, the data set coming from the soil grid over here, they are over here, where they have presence of soil moisture, soil content, and so on. So this is the data set, the table that is going to be, that's why it's million of row, where the machine learning is going to perform and identify the different correlation. So we build up over here. We saw over here these two aspects. Now it's missing the gauging station that we have all over the world. So probably some of you already know, but the GSIM is a data set that was coming out last year. There are 2 publications with a very high accuracy and quality control procedure that has been implemented, and it's going to be 30,000 around the globe by integrating all the different data sets. And of course, you can see that probably because I need to check everything, we are really covering the full ecoregion. So we are covering it, especially with the United States and with Brazil and Europe. We are covering all the tropical, subtropical, savanna, and subtropical, subarctic, and so on. So we are going to really have a big number of data where we can implement machine learning. The beauty is that this data set is releasing mean and minimum, maximum standard deviation, minimum of 7 days, maximum 7 days, and the best about 10 and 20. So in theory, we can rebuild the complete PDF, probability density function of each month for the stream flow. So we are sort of modeling the monthly level, but almost a daily. Because we don't know where it's happening, but it's going to be from this mean to this maximum, reaching this situation. So it's like sort of modeling the daily. And we are going to use different kind of procedure from identifying training and testing between using the GSIM quality control indices, different kind of cross-validation for the testing and training, probability sampling in terms of spatial kernel density for sampling in according to the probability, sampling in according to the stream order and the ecoregion in order to see if we are able to cover all the different potential situation. And we can also implementing an external validation procedure with a camel data set that has been not seen completely from the machine learning training, and to see the efficiency of the machine learning. So so this is the three fundamental aspects for the machine learning in order to work. And this is where you have the machine learning. So you have your Y, that is going to be for example, the quantity, where you are going to have all the different predictors for all these, with all the observation for all these gauging stations, and you are going to build up this algorithm. You are going to estimate the different predictors that, due to the machine learning attitude, they are not going to be just a single coefficient, but is a coefficient that is changing in according to the different dimension of the data set, of the predictors. And the data set that I'm going to implement is a 10 terabytes. I'm estimating 10 terabytes to build up all the different predictors that we are. Probably this one is going to be, the preparation of the data set is going to be longer than the real modeling. Because probably the real modeling is going to be to run the model, probably maybe a few days, but then you have to see the accuracy and go back if something is wrong in the accuracy, to go back and see if there is something wrong in the predictors. Because the machine learning usually is very sensitive. If it's a good training data set, you will get good results. As soon as there are errors, that error is going to influence everything, or at least some part in the accuracy. So this is something that we need to take account doing some different double check. So how we are going to build up this one? By combining under the supercomputer at Yale, combining really different kind of language integration, going from the climate data operator for all the net CDF and with an NCO, OAK for text manipulation, GRASS for stream network and variable accumulation, PK tools and GDAL for all the different preprocessing of the data set, Orfeo toolbox for some Landsat satellite application that we need to figure out if something is missing, and R and Julia for all the modeling part. In particular, Julia probably is going to be our candidate for the machine learning due to key speed and potential. Under the spatial ecology framework, I'm teaching also with other colleagues to geocomputation intensive training to training the student to the big massive computation under Linux framework, and implementing in for machine learning in hydrology. This is something that we are trying to run every year at two locations, one in Europe and one in the United States. Now let's see what some result in water quality application that is going to be, let's say, a good proxy of the result for the stream water analysis. So this is a work that I've done in combination with Long Shen a clever guy, a chemistry guy from, he's now in Cambridge, estimation nitrogen phosphorus concentration in contiguous United States from stream, and is going to be, is under review in scientific data. So we have observation of nitrogen phosphate in the United States coming from the water quality United States data set, so like 200,000 stations, more than versus all the stream network that I just described. So at 1 kilometer resolution. We have random forest model. So if we build up, we run the process and we build up all the machine learning. We make the prediction in engaged location. So we having this beautiful map of the concentration of total nitrogen, total phosphorus in the United States. And you can see immediately, pop up immediately all this area that is the agriculture, like the over here in California, but also not only agriculture, but also all the urban that influence in New York and DC area that influence the high concentration of nitrogen, high concentration of phosphorus, and we are reaching the accuracy of 70% in each stream in the United States for prediction. So this is a quite appealing result, something that so far has been done only locally. Now with the machine learning framework, due to the predictors in direct relationship, we are able to compute the accuracy. So in the same framework, with the same thinking, we are going to build up for the quantity of water. And sometimes machine learning has always been criticized as to be not able a black box. But we are trying to think in a different way, not with a classical statistics, then something can come out. So I like to always make these with examples. So and discover hidden correlation in machine learning output. So this is the typical random forest output where you have the ranking of the variable, which one is the most important. So if you take the first one, that in our case is agriculture, and you predict agriculture versus one of these, so you obtain just a cloud. Okay, so if you do urban build-up, land cover versus total nitrogen, and this one is going to be the first variable, you obtain just a cloud, R 0. maybe 1. Okay, why? Because the machine learning is not working in 2D, it's more working in a multidimensional framework. So how we are going to map in another way is to see something useful. So if you do a lot, rather than do a full personal coefficient, you do a local personal coefficient. So you do a personal coefficient in a moving window that is moving around the United States. You can see that the total nitrogen in some area is high correlated, okay, with the land use. In some area is complete with the land cover in the agriculture. In some area is completely opposite. Some area in the center, this value over here, so all this area this area transition area is uncorrelated. So what does it mean? That another variable is going to be the correlated one. So this is a way that we need to use it to interpret the result of machine learning, because with the classical interpretation, no way you can get anything. Okay, this one you have to think in a three-dimensional, in multi-dimensional way in order to understanding the output of machine learning. So also this one probably in September should be out. Anyway, they are already in preprint. You can already reading in the different application. So and this is the beauty of machine learning, that with the same framework we will be able to predict the flow at this point per second, but also the nitrogen and the phosphorus for concentration. And this is quite appealing also, for example, for the carbon, because we can get also the concentration of carbon. And then from the concentration to the emission, you can have a physical model in that case that, based on temperature or the parameter, is transfer the concentration from the water inside to the emission into the atmosphere. So this is something that we are working, especially now with the nitrogen, going from concentration of nitrogen to the emission, and in carbon, in the future we wrote a grant from carbon to carbon concentration to carbon emission from stream. So, and in terms of stream, what we want to get? We want to get for us one specific point. We want to have happening what is happening in the past. So we have over here the here and here the meter cube per second, what is happening in the past for each single year, and that more or less we want to go at monthly level, and maybe in the future also daily level, and be able to extrapolate for each stream this graph in particular. So let's see what we are so far though for the Flow 1K data set. So we have been loading this data set in this web frame that we are building with a third party with open land. So the Flow 1K allow you to really click in any specific location of the world. Okay, so you can see that they overlapping the stream, and if you click in one specific point, you can get the estimation of each single year, but we are missing information of the month. So we want to go one level deeper in the temporal analysis and in the spatial analysis, because this one is 1 kilometer, we want to arrive to the 90 meters. And of course, over here, you can get the trend, and you can get also the graph that to show you when is going to be the flooding period or so on. So if you are able to arrive at 90 meters at monthly level, then we can really having a good information for the stakeholders in flooding risk events and also water mitigation in general. Sorry? Water? Over here is meter cube per second? No, sorry. Yeah, this is meter cube per second. Yeah. Height of the water? No, but indirectly with the same procedure, you can estimate also water depth. So again, if we have observation of any kind of element, and we have good predictors, where we can modeling even the water depth. One of the, for example, one of the immediately thing that we are going to do it is modeling water width, because from satellite information you can get the growl data set that has been from George Allen has been produced over here. He can arrive to 30 meters, but below 30 meters you have to go in prediction. And over there, machine learning can help to predict everywhere the width. The depth is going to be same kind of approach, but yeah, would it be possible? Of course, some like the depth will be high uncertainty, rather the width is going to be much better to simulate. Yeah. Okay, so just coming up to some conclusion, this is the team that I'm working with, different kind of scientists with very, very, very strong in coding. As you can see, is one of the main part of this work is really massive data process for the computation aspect and also from the modeling part. So I'm dealing mainly with the open source software, all this open source software like GRASS, GDAL, PK tools, R, Python in the HPC environment. Lunzu Shen is a data science and chemistry modeler with a strong Bayesian and machine learning approach, able to dealing with the C++ and Julia for the massive computation. Holger Viro is the PhD student that is building up the data set for the water quality at global level, like the GSIM for water quantity is doing for water quality. Sami Domisch from Germany, from Freshwater with GRASS and R in high-performance computer environment, and Jens Kinesel with hydrology and GDAL computation, and Tushar Sethi is an exclusive level relationship, able to talk with stakeholders for communication strategy and also to decision-making aspect. So in few conclusion, we are really implementing a machine learning framework that allow the prediction of freshwater discharge and freshwater quality as a geochemist. In particular, also hydrology feature for engaged location. And this one in particular, hydrology feature, can be important for the SWOT mission, because in the same concept that we are using to calculate the water quantity, I can use it also to calculate friction parameter that later on can be ingested inside the process-based model to arrive to this concept where process model and machine learning, they can be integrated together. And then the same for example, residence time, because we have between the station, we have distance, and we can calculate the speed and the total residence time. And we are building a WebGIS interface that we show a preliminary result to support the decision making in general, to bring this information also to other countries. These are the preliminary work, geomorpho 90 meter with the 1026 variable that I was described, and NMP concentration that are under review scientific data, but they are already in preprint in PRJ journal. Yeah, these are my contacts that you can follow me on Twitter or in spatialecology.net, where we sponsor some activity in coding, in geocomputation, and machine learning. Yeah. So open question, the floor for you.
Yeah, I have a question.